This is problem 5-46. It is on page 305. There's a description for the problem, but it's just a lot of figures basically with different problems you could work. My goal is to compute the reaction forces. We've got a beam that has a 12K load, which I assume is 12 kips. There are reactions at either end of the beam, at A and B. There's also a distributed load that occurs, and it is 2.5 kips per foot. There's another concentrated load of 10K. Now, the position of all these loads are 3 feet between A and 12K, 3 feet between 12K and the distributed load. The distributed load, there's 4 foot of this 2.5 kip per foot distributed load, then the 10K load, and then another 4 feet to the reaction at B. And so my goal is to create the shear and moment diagrams for this beam, as well as finding the reactions. So let's begin by finding the reactions. And what I would recommend you do is sum moments at both A and B. And then, excuse me, when you do that, you'll find the reactions at A and B, which then you can add them together. In other words, sum forces in the y direction. Make sure that you haven't made a mistake in the moment calculation, because it's easy to make mistakes along the way. Anyway, for B, if we're summing moments about A with counterclockwise being positive, I'll start from the right. Essentially, we have 14 feet multiplied by the load at B. That's the moment caused by that force. Then, if we consider the 10K load next, that's a moment in the opposite direction. 3 plus 3 plus 4 will give us 10 feet multiplied by 10K. So that's a negative moment due to that concentrated load. What about this distributed load? Well, the distributed load is causing a negative moment. And what we really need to do is take the resultant. The resultant is going to act in the center of this distributed load since it's uniform. And so that's another 10 feet. But then the load is going to be 2.5 kips per foot times 8 feet worth of that load. So let's just write it that way. 2.5 K per foot multiplied by 8 feet. So there's the moment due to the distributed load. And finally, we'll have minus the moment arm of 3 feet for the 12K load. Now all of these, the moment of all this comes to 0. If you solve for B, what you'll find is that B, the reaction B, is 24 kips. So let's write that down. Now let's sum moments about B. Check my notes to make sure, because I wrote some of that on the fly. Yeah, that should be fine. Okay, summing moments about B to find the reaction at A. Well, I'll start all the way at the other end of the beam again. So let's see, if positive is counterclockwise, then A is causing a negative moment, at least according to my assumed direction. Notice we don't know that that's correct yet, but of course, if you have enough intuition, you know it's going to be right. So negative 14 times A plus 11 feet times the 12K load. Why? Well, the 12K load, if we look where it's at relative to where we're summing moments, 3 plus 4 plus 4 is 11, so that's where that comes from. That takes care of A, the 12K load. Now let's take care of these two loads. And the next one I worked with was the distributed load. The distributed load is going to cause a positive moment, so plus the magnitude, 2.5 K per foot multiplied by 8 feet. Okay, so 8 feet is this is just getting the resultant, so for 8 feet times the 2.5 K per foot. And then the moment arm is going to be a 4-foot moment arm, because that's where the resultant is located of this force. Turns out that also the 10K load is 4 feet away from the point where I'm summing moments. And all this comes up to 0, so there's my equation. Notice A is the only unknown. If you solve for A, what you find is that A is equal to 18 kips. So let's write that in. So 18,000 pounds. Okay? Now, if we sum forces, what happens? Well, let's sum forces in the y direction. Well, let's see, we've got 18 and 24 acting upward. We've got 12, 10, both acting downward. We also have the distributed load, which is 2.5 K per foot, multiplied by 8 feet. When you add all this up on your calculator, at least when I did it, I got a 0 now. Forgive me, I haven't used units on these other terms, but they're all kips. So we've verified that we've got the correct solution for the reactions. Okay, that takes care of that part. The next part of the problem is to create the shear and moment diagrams and be able to tell you anything you wanted to know. So we'll need to know shapes of curves and things as well. Let's draw the shear diagram next. I'm going to move the shear axis off to the side just a little bit. Let's see, I want to leave myself enough room for the moment diagram. Just a little more, I guess, space. Okay. So the x-axis will be measured in feet. And we're going along, there's no beam, so there's no load until we get here to this point. Now, understand what we're doing is we're saying, okay, the beam has this reaction force of 18 kips, and so the shear would have to be down in this direction to keep the segment in equilibrium. Okay, notice we're just talking about a very short segment at the beginning of the beam. So the shear goes up immediately to 18 kips. Now that shear is going to be constant. Notice it doesn't really matter how much of the beam I take or how far I consider a cut in the beam, the shear force is going to be 18 kips. So that remains constant until we get to this point. Now, when we get to the point where there are 12 kips applied in the opposite direction, well, now the shear only needs 6 kips, right? Notice that's the difference. Notice what we're doing. All we're doing is we're going to go down by the 12K load. So we'll go down. So this height here is 12. Scale's not real good, but hopefully you get the idea. So we come down to 6 kips of shear. Okay, that's going to go along constant until we get to the distributed load. And at the distributed load, what will happen is the distributed load, as we cut farther and farther into the beam, is going to add more and more, or resist more and more of this force. We've got 12K against it, but it'll start helping us out a little bit. And in fact, will help us out continuously. So the curve will look something like, let's see what about there, will look something like this. It'll be a straight line, and the slope of that line is just 2.5 kips per foot. Now, we'd like to know where the crossing occurs. But what is the crossing? Well, the crossing is where we've got just enough of this 2.5 kip per foot load, is how many feet, let's call that x, we need, so that we need no shear, so the shear is 0. It's not a very good shear vector. So where does that occur? Well, basically, remember the shear was 6, right? The shear was 6. We need to eliminate 6 kips worth. How many feet at 2.5 kips per feet does it take to eliminate 6 kips? Well, if you plug it into your calculator, what you'll find is that you only need 2.4 feet. If you multiply 2.4 by 2.5, you'll find the answer is 6. So this distance, x, is 2.4 feet. So this position on the x-axis along the length of the beam is 2.4 plus 3 plus 3. So that's 8.4 feet. That's where the 0 crossing occurs. That's where the shear is equal to 0. Okay, so it continues going down until what? Well, until we reach this 10 kip load. Well, how far has it gone down? Well, there's 2.5 kips per foot times 4 feet. Okay, so if you do the math, what you'll find is this comes down to -4 kips. Okay? So let's see, how do you figure that out? Well, 4 times 2.5, 2.5 and 2.5 are 5, 5 and 5 are 10. So there's a change of 10. Now don't be confused, it's not this 10. The distributed load from here to here accounts for 10 more kips. So if we were at 6, we're going to move down to -4 for a total change of 10 kips. Okay, now at this point there's another 10 kip load, which is a point load. That's going to move us down even farther, because understand now we're at the point where we've got this 10 kip load. What does the shear have to do? Well, if you sum forces, you'll find the shear will have to be in the negative direction. Remember, shear on the right-hand side of the beam up is negative, down is positive. And so how far does it go? Well, just by the change in the load. So this will go down to, let's just put it here, -14 kips, because -4 minus 10 is -14. And then what? Well, the distributed load continues to add. So we just move down at the same slope that we were before. How much? Well, another 10 down, which will take us down to -24. I'm going to cheat just a little bit and move this up so I have enough space later. -24, so there's our -14 point. And sure enough, at the end, there's a load that brings everything back to equilibrium of 24 kips. So there's the shear diagram. Where is the shear the highest? Well, it's the highest right over here. It's pretty high on the left-hand side, but again, shear is usually not what causes failure in a beam like this. What causes failure is the moment. So let's come up with the moment load. Okay. The moment will be in kips, or well, really feet kips. Record our position along the beam in feet. The moment at the left-hand side, there are no external loads applied, so the moment begins at 0, which is not a surprise. And remember that the moment is just the integral of shear as you move along the beam. That's what this dx says. It just says as you move along the beam, add up all the contributions to the shear. So it's just the area beneath this diagram. Now notice that this area increases linearly because the shear is constant. Okay? So if we multiply 18 by 3 feet, then we will find the magnitude of the moment at that point. When I did that, I found that it was 54,000 foot-pounds. So that's a linear line, just going up to 54. Then we have to add more area, so there's another rectangle here. It's easy to calculate areas of rectangles. Notice that the line that comes up, the moment line, is not going to be at as large an angle because, or as steep an angle, because the magnitude of the shear, which represents the angle, is lower. So the amount of moment added will be 6 multiplied by 3 feet. So that's 18. 18 plus 54 comes out to 72. So when I draw my moment diagram, this point is 72 because I've added 18 foot kips worth of moment to the 54. And notice it's a linear line again because this is a constant shear, but it's not as steep as initial because it's not as much shear per foot being added. Okay? Now, notice this little segment here. It's basically a triangle. And so if we want to find out where we end up, all we have to do is add the area of that triangle, which is pretty easy. So it's 2.4 feet multiplied by 6 divided by 2. When you add that up, you find that it's, when you add the result of that to 72, you find that the total is 79.2. Let me put it beneath. That's too small. So 79.2 foot kips. And notice that the shape of this curve is different, right? This portion of the curve has to be concave down. Now, the equation of this portion of the line, the shear, would be a linear equation, right? It would be first order in x. When you integrate something that's first order, you end up with something that is second order. So we expect this curve to be second order. Now I'm not going to write that down because later on we'll actually perform the integration and show that this is true. Anyway, continuing, notice that basically we're just adding negative area now. So this is a maximum. Okay, so it's a maximum where the slope is 0. That's not a surprise. The slope is represented by the shear. So right here, that slope is 0. Now notice we're adding more and more area as we move along, so we expect this to be concave down. Or we're taking away more and more area. Well, how much do we take away? What is this area? Well, if this distance is 2.4 and the total distance is 4, then you can see that my scale is off, right? And this should be a smaller triangle. In fact, the area of this triangle, let's see, if this is 2.4 and this is 4, this is 1.6, would be 1.6 feet multiplied by the height, which is -4 divided by 2. That's the area of that small triangle. When you add this to the 79.2, you come out to a moment of 76 foot kicks. Okay, so then what? Well, then we have a little bit more negative area to add. Notice that this area is moving downwards, so we expect this again to be a second order curve. That's first order, so this will be second order. And we hope it comes back down to the axis. So I hope this area is 76. Let's find out. How do you calculate it? Well, the easy way is to take 14 plus 24 over 2. Notice this gives me the average height, multiplied by that length, which is 4 feet. When you calculate that, plug it in your calculator, you'll see that you do come out with 76. That's 76 negative area that has to be subtracted from the 76, so we end up back on the axis. Now, we still don't know all the details about these that we might like to know. For example, it would be nice to have an equation for this segment, and for this segment, and for these curved segments. The straight segments are pretty simple, so I won't bother with those. But I will work with this section where the moment diagram is curved. Before we get into the moment, though, we need to come up with equations for the shear as a function of position. Now, I'm going to work with the position from 6 feet all the way over to 10 feet. Okay, so I'm working with this segment here. So x between 6 and 10 feet is what I want to deal with. Now, how do you come up with an equation for this? Well, what I do is I just begin with the slope. What is the slope? Well, the slope here is just 2.5 kips per foot, and it's a negative slope, so negative 2.5, and I won't write down the units, and then multiply that by x, and then I'll just put in an offset so that one of the ends is correct. For example, on this end, I need to get 6 when x is equal to 6. Okay, so when x is 6, plus some constant, I need to get 6, right? Because this, I'm just trying to come up with the equation of a line that represents this line. Well, okay, no big deal. So if you solve for the constant c, what you'll find is that that constant is 21. Basically, you have to multiply this out, add it to both sides, of course, and you find c. So let's check and make sure that works. We know that it works at 6, but what about when x is equal to 10? Okay, well, v of 10 then is negative 2.5 times 10 plus 21. So let's see, that would be, make sure I'm thinking right, yeah. So 10 times 2.5 will be negative 25 plus 21, sure enough, is negative 4. And so now we verified that we have the proper equation for this line. So that works out. Now, there's the shear in that section, but what we're really interested in is the moment. That's the difficult part, right? What is the moment in this section? Well, the moment is just the integral of shear. That's all it is. Okay. So that means we need to integrate negative 2.5x plus 21 dx. Well, that's easy. That's just negative 2.5x squared over 2 plus 21x plus some constant of integration. Notice I don't have limits here, So I have to add that constant of integration. And then again, I'll just plug in the end conditions to figure out what the constant of integration is and then verify at the other end. So if we plug in, let's see, a moment of x equals 6 feet, I'll make that clear what I'm plugging in. So the moment at x equals 6 feet, in fact, let's do it this way. X equals 6 feet would be negative 2.5 multiplied by 6 squared over 2 plus 21 times 6 plus c. Okay, now we know what the moment should be at 6 feet. It's right here. It's 72. So if you solve for c from this, what you'll find is that c is equal to negative 9. Okay, so I'm running out of space. Let me jot down the result up here. So the moment as a function of x is negative, let me simplify this, 2.5 over 2 is 1.25. So x squared plus 21x plus c, but c is negative 9. There's the moment as a function of x. Now let's verify that that works, because that should give me the moment at any point that I want it, right? So let's go over here and check this point. So the moment at x equal 10 is negative 1.25 x squared plus 21x minus 9. When you plug all this in, you'll find that this is in fact 76, and so we're sure that our moment equation is correct. You could plug in this point as well. You could plug in x equals 8.4 feet. When you do that, you'll find that the moment is 79.2. So our equation works out just fine. And so there's the shear and the moment in this section from x between 6 and 10. What about when x is between 10 and the end, which is 14 foot? What happens in that section? Well, let's see. We need a different equation for the shear, because while the slope is the same, the offset is different. So for that section, obviously, since the slope is the same, we'll still have our negative 2.5x, but now the constant at the end will be different. So if we plug in v of 14 equals negative 2.5 times 14 plus the constant, well, the shear at 14 at the end should be negative 24. And so what that tells us then is that the constant must be equal to 11. And so plug in 11 for that constant, and then we'll check. So what happens when x is equal to this point, which is 10 feet, 3 and 3 and 4 are 10. What happens when we use that constant of 11? Well, then we actually come out with negative 14. You can do the math, right? This is negative 25 plus 11 is negative 14. And so we verified that this is the correct equation for x between 10 and 14 feet. So now we have the equation of that line. So let's integrate it. Why do we want to integrate it? Well, because the moment is the integral of the shear. And so integrating negative 2.5x plus 11 dx, we find that this is negative 2.5 x squared over 2 plus 11x plus some constant of integration. Okay, plug in the boundary conditions again for this, or the end conditions. At x equal to 10, we should end up with a moment of 76. So let's see. At 10, negative 2.5, 10 squared over 2, plus 11 times 10 plus c, we should end up with 76. Okay? So if we solve for that constant c, what you'll find is that that constant comes out to 91. Okay, so now let's plug that in. So negative 1.25, again simplifying the 2.5 and the 2, x squared plus 11x c plus 91 gives us our moment equation. We need to verify that this works in this section. Okay. So we've used, let's see, which point did we use? We used 10, so we should verify. Moment of x equal 14 feet is negative 1.25. 14 squared plus 11 times 14 plus 91. When you write all this out, you find you get a moment of 0. And so this checks out, right? Because we should end up at 0. All right, so what have we done? Well, we've solved the problem. We know the magnitude of the moment and the shear at any point in the beam. We've got equations to represent the difficult parts, and that's the end of the problem.